So let's see the order statistics on the minimum of independent random variables. So here we are going to assume that x1 and x2 are two independent random variables, and each of these independent random variables will have its own cumulative distribution function. And we have fx1 here and fx2 here, which respectively shows the probability of the x1 random variable to be less than or equal to x and x2 random variable to be less than or equal to x. So these two random variables are independent, and we are defining a third random variable which is equal to the minimum of x1 and x2. So what does that mean? Imagine you have an automobile, and the automobile will stop working. Either it has a breakdown related to its engine, or let's just say it has a problem with the clutch, okay? So the gear. So either we will have an engine problem or a gear problem. And this means what? The car is going to stop when one of these two components break down, either engine or gear, okay? So the lifetime of the automobile is equal to the minimum of the lifetime of these two components. And since x1 and x2 are both random, the lifetime of these two components are random, we can say that t can be equal to x1 and as well as it can be equal to x2 as well. So which one, engine or gear, which one breaks down first will determine the lifetime of the automobile, okay? So therefore, the lifetime of the automobile is random as well, dependent on the lifetimes of these two components. Actually, in an automobile, we have several components. We cannot simply determine the lifetime of an automobile based on the two components only. We have several components, but we are trying to simplify the example here. And here, we are interested in the probability distribution of t, the minimum of these two random variables. And in order to identify that probability distribution, we mainly intend to compute the cumulative distribution function of t, which is the probability of t to be less than or equal to an arbitrary x. Now, I can calculate that probability, the probability of the lifetime of the automobile to be less than or equal to x, as the probability of the minimum of x1 and x2 to be less than or equal to x. So I will simply replace that t with its definition, which is minimum of x1 and x2 to be less than or equal to x. Now, if you have studied the previous videos, you may know that how we are going to continue from this point. But here, you will realize that the fact that the minimum of these two random variables to be less than or equal to x does not require both of them to be less than or equal to x. So we are interested in the minimum of these two random variables to be less than or equal to x. The maximum can be greater than x. It doesn't matter. Therefore, we cannot simply separate this expression as both x1 and x2 to be less than or equal to x, because it's not a necessary condition. However, if you rewrite this probability statement using its complement, which means if you rewrite this probability as 1 minus the probability of minimum of x1 and x2 to be greater than x, in that case, you will realize that the minimum of x1 and x2 to be greater than x will require both of these random variables to be greater than x, or in other words, if both of these random variables are greater than x, automatically their minimum is going to be greater than x as well. So when you are dealing with the minimum of random variables, it is always a better approach using the complement events probability to determine the cumulative distribution function of the minimum of these two random variables. Now you see, if we rewrite the minimum of x1 and x2 to be greater than x as x1 to be greater than x intersection x2 to be greater than x, then we know that according to our assumption, these two random variables are independent. Then the joint probability can be expressed as the product of the individual tail probabilities. So probability of x1 being greater than x times probability of x2 being greater than x. This product must be subtracted from 1. Now, these two tail probabilities here can be computed by subtracting the CDF of x1 at x from 1, and the second probability here can be computed by subtracting the CDF of x2 at x from 1 again. And finally, we have this final formula for the CDF of the minimum of two random variables. Now let's practice this. If you remember question 9, we have two batteries with independent lifetimes. The first battery has an exponentially distributed lifetime with rate of 1/3. And x2, the second battery, has an exponential lifetime with rate parameter of 1/5. Now remember, these lifetimes were given in days. So the average lifetime of x1, the expected value of x1 is 3 days, and the expected value of x2 is 5 days. So the second battery with a lower rate parameter has a high probability, most probably a higher probability to have a higher lifetime. But it doesn't matter which one is higher or not, because they are both random. X1 as well can be the battery which has the largest lifetime because of the randomness. And suppose now we have a device which is to which we are going to attach these two batteries, and the device will stop working if one of the batteries completes its lifetime. So the device will stop if any of the batteries will stop working. What is the probability that the device will stop working in less than 2 days? Now this time, if we define the lifetime of the device as y is going to be equal to the minimum of x1 and x2. And the question here is asking the probability of the lifetime of the device to be less than or equal to 2. So if either one of the batteries stop, then the lifetime is going to be equal to the minimum of these two lifetimes of these batteries. Now, as we have done theoretically, trying to find the probability of y being less than or equal to 2 cannot be very practical. So we are just going to find the tail probability, the probability of the lifetime of the device to be greater than 2, because this inequality, the minimum of the x1 and x2 to be greater than 2, requires both of these random variables to be greater than 2. So we are going to calculate the probability of y being greater than 2 first, which is the probability of the minimum of the lifetimes of the batteries to be greater than 2. And that requires both of the batteries to have a lifetime that is greater than 2 in an intersection event. And since these events are independent, because the random variables are independent, the lifetimes of the batteries are independent, we can rewrite this joint probability statement as probability of x1 being greater than 2 and times probability of x2 being greater than 2. Now, both x1 and x2 are exponential random variables, and such tail probabilities can be computed by the tail probability function, which is e to the power minus lambda x. And here, x values are simply equal to 2, and the lambda values are respectively equal to 1/3 and 1/5 for both batteries. So when we multiply these two tail probabilities, we get 0.3441. As this tail probability, the lifetime of the device to be more than 2 days is 0.3441. However, remember now the question is asking us what? The probability of the lifetime of the device to be less than or equal to 2 days, which is the complement event of this. And we will simply subtract the answer that we found here from 1, and that is going to give us a 0.6559. We can simply say that approximately with 65% probability or 66% probability, the lifetime of the device is going to be less than or equal to 2 days. Now, we are going to generalize the minimum of n random variables to more than 2 random variables. Actually, the logic is the same. In fact, instead, we are going to observe multiple random variables here. Again, they are going to be independent. Imagine now there is a device. This time on the device, we are attaching multiple batteries, not just two of them, but n of them. But each of the lifetime of these batteries are independent from each other. And each battery has a different cumulative distribution function, let's just say, okay? So fx1 represents the probability of the lifetime of the first battery to be less than or equal to x. fx2 represents the probability of lifetime of the second battery to be less than or equal to x, so and so forth. Now, we are defining t this time as the minimum of these random variables, x1 to xn. This means if any of the batteries die out, if any of the batteries exhausted, then the lifetime of the device will be terminated. The device will stop working. So this time we are interested in the probability of t, which is defined as the minimum of multiple independent random variables, and this cumulative distribution function of t is the probability of t to be less than or equal to x. And we replace t as the minimum of x1, x2, and xn, all of these random variables. Remember now, the fact that the minimum of these random variables to be less than or equal to x does not necessarily require all of them to be less than or equal to x. Maybe one of them, maybe multiple of them can be less than or equal to x, maybe all of them. So in any way, the minimum of these can be less than or equal to x, but that does not require all of them to be less than or equal to x. But if I rewrite that probability from the complement events probability as 1 minus the probability of the minimum of these random variables to be greater than x, then the minimum of these random variables to be greater than x will require all of them to be greater than x respectively. So the intersection of all of these greater than events is the same as the minimum of these two to be greater than x. So in other words, if the minimum of these are greater than x, this means all of them are greater than x. If all of them are greater than x, then automatically the minimum is also going to be greater than x. So this expression and the below expression, which is written in the intersection format, is the same. Now we know that these random variables are independent. Therefore, this joint probability of multiple random variables can be rewritten as the product of the individual tail probabilities, the probability of x1 being greater than x, the probability of x2 being greater than x, so on and so forth. And each of these tail probabilities can be computed by subtracting the cumulative distribution functions at these points from 1. So we are basically generalizing the minimum distribution for 2 random variables to n random variables here. And in this question, we are going to practice it. Let's just say we have 3 random variables which are independent from each other, and they are identically distributed as a standard uniform random variable, which means their lower bound parameter is 0 and upper bound parameter is equal to 1. So y is a random variable which denotes the minimum of these 3 random variables. Since all these 3 random variables can take values within the 0-1 interval, y is also taking values within the 0 and 1 interval. Because it is defined as the minimum of these 3 random variables, most probably the value of y is going to be a lot closer to 0 than being closer to 1, right? If y was the maximum of these 3 random variables, then you would have seen that y is going to take values most probably close to 1, but less probably to close to 0. Now, in this case, because it is defined as the minimum, we expect lower values than higher values within the unit interval. Now, y is defined as the minimum of these random variables. Part A asks us to compute the cumulative distribution function of y. Now, actually, the formulation is given here. The final formulation for the minimum of these random variables is given here. We can directly use that to compute the cumulative distribution of y, and then we are going to compute the probability of y being greater than 0.5. Now, the cumulative distribution is what? For each of these random variables, it is simply equal to the identity function within the unit interval, because we know that the cumulative distribution function for uniform random variables is equal to x minus alpha divided by beta minus alpha. But if you plug in the specific parameter values 0 and 1, you would get identity function x for all these three cumulative distribution functions, because these random variables are identical. They follow the same distribution. They are both standard uniform. Now, the minimum of these three random variables y has the cumulative distribution function equal to 1 minus the product of the tail functions. So we are subtracting the CDF from 1 for all of these three random variables, and the tail functions will be multiplied, which will bring us a 1 minus x to the power 3. And when we subtract 1 minus a parenthesis to the power 3 from 1, we are going to get the cumulative distribution function for y. That is the minimum of these random variables. And since the question, second part of the question, asks us the probability of y being greater than 0.5, we are going to compute it by subtracting the cumulative probability of y at 0.5 from 1, because this is a tail probability, this is a cumulative probability, and they are the complements of each other. These two events are complements of each other. So 1 minus the CDF value y at 0.5 means 1 minus 0.5 to the power 3. You are basically plugging in 0.5 value here, and you are additionally subtracting that function from 1. And that probability will be equal to 0.125. So as I have said, it is less likely for the minimum of these three independent standard uniform random variables to be greater than 0.5, but it is more likely to be less than 0.5, which is 0.875 in that case. Okay, that's the end of this chapter, my friends, and your reading assignment is described here. So you have a 4-page long reading assignment from the textbook of Ross at these pages, and again, a similarly short section in Montgomery's book. We are going to move to the next chapter